See, this conservation of energy and energy equation, as we mentioned that this equation will be required when we have a considerable change in temperature in the flow. If it is not, then of course, this equation will not be required. And we have already mentioned that most of this course or rather this course fully and even the next course we will consider incompressible flow without much change in temperature. So, this equation will not be required for this course as such. However, later on it will be required and used, and you have to remember this equation without using it for the time being. Because I would like to complete the governing equation at this stage. It could have been left for later use or later application and could have been derived later when you are going to use it, but since we are deriving the equations, we would like to complete the derivation at this stage. As you know, the first law of thermodynamics usually we call a statement of energy conservation. The first law of thermodynamics, as it states that the internal energy of a system changes due to the work done on it and due to the heat added to it. So, if there is a system and you add heat to it, you would do some amount of work on it, then its internal energy will change and the change in internal energy will be given by the sum of the work done on it plus the heat added on it. Okay. So, using that conventional notations, the first law of thermodynamics says the mathematical statement will write, say change in internal energy is equal to the sum of the work heat added plus sum of the work done. Heat added to the system plus work done on the system. Of course, in this application we will consider that system is the fluid, the moving fluid, that is the system here. Now, as were mentioned earlier that the thermodynamical laws are derived or postulated for system in equilibrium. The system is in thermal and mechanical equilibrium, and we stated that the moving fluid is not in that sense a system in equilibrium, in thermal and mechanical equilibrium. It is not in that sense in equilibrium. However, looking into this rate of change in internal energy is sum of the heat added and sum of the work done. Now, the amount of heat added or the amount of work done, they are of course can be measured, and see whatever is the sum, if we consider that as the increase in the energy. So, whether it is a system in equilibrium or not, we need not be that worried. We can even consider that even though the system was not in equilibrium, but it was passing through a successive stages of equilibrium, and we can use this relation even for non equilibrium. Only perhaps change that we need is that while considering this energy, instead of treating it just an internal energy, we should treat it as the energy, and moving fluid has energy other than the internal energy. particularly its kinetic energy. Particularly its kinetic energy. So, this energy we can think of as the internal energy plus the kinetic energy. Now, let us look to the different terms in it. Let us first start with the work done. The work on the system, in this case the system is, as you say, the system is subjected to two different type of forces, the body forces as well as the surface forces. And obviously, both, if we consider a very small material element of fluid, moving fluid, then both the forces will do some amount of work on it. So, let us start this term by term. First of all, let us consider the work done on the moving fluid system. This will be by body forces and surface forces. Assume a small material element of delta tau once again. So, how much will be the work done on this material element by the body forces? See, the total body force is rho f I d tau. Work done is a scalar product of the velocity and force, rate of work done. And the scalar product in our initial notation we write like this. Okay. So, this will be the rate of work done. Okay, we will be happy with rate of work done, rate, for all the term, because the original equation, the first law of thermodynamics, can also be expressed as a rate equation. It was just expressed as a change equation, but we can express it as a rate of change equation, that all the term, instead of just writing simply d, we can write is d dt of E. So, this rate is fine, no problem. Now, what will be the work done by the surface forces? Again, of course, rate of work. Yes, how much is the total surface force? if the surface bounding this element, the surface of this element d tau delta s as we are writing, then the total surface force is as before sigma I j n j d s, and again a scalar product with the velocity. So, this will be u y sigma I j n j d s, and if we add the two, we get the total work or rate of total work done by the forces. However, there is a difficulty in adding the two terms, one is a volume integral, other is a surface integral. So, once again we have to express this surface integral by volume integral using that divergence theorem, and that is quite obvious, quite easy. What it will be? Okay. So, the total work, and okay, you can the rate, we are not writing that word rate. So, total work by the external forces. Which again can be written as okay. From the first two term, you see what it is. We can take out the u I. From the first two term, we can take out the u I. Okay, the first term is the work done by the body force, and okay, let us before going that complete it. what is this rho f I plus d sigma I j d x j? Look back to the Navier-Stokes equation, the most general form of the Navier-Stokes equation, where we have not replaced sigma I j, and this is the right hand side or the force acting which is causing the change in momentum. So, this term in the bracket is actually what is d u I dt, rho d u I dt, the left hand side of the Navier-Stokes equations. So, this is okay. See, even this first term now can also be expressed as this. Yes. This is what? The entire term is of course the rate of change of kinetic energy per unit volume, kinetic energy of the bulk motion. Okay. Not the kinetic energy of the molecular motion, because you are thinking in terms of energy equation where internal energy. So, we should differentiate that. All of you must be well aware of that what we call is internal energy is also basically a kinetic energy, but kinetic energy of the random molecular motion. Okay. It is not that, it is what is the flow velocity. So, what we are calling flow kinetic energy. So, looking to this now, looking back, these two terms, this first is from the body force, of course, the work done by the body force or the volume force, and this is also a part of the work done by the surface forces. This is also another part of the work by the surface forces. The surface work by the surface force has two terms in it. The work by the surface force has two terms in it, these two, and this one part has gone to this kinetic energy term. So, you can see that the volume force along with a part of the surface force is responsible for the change in the kinetic energy of the bulk motion. But what about this term, what it is? Think in terms of the element, a small element d y j d x j is expressing at change in velocity across the surface, across that material surface, and sigma I j is the stress acting. So, it is basically expressing a deformation of the element. This work is equivalent to a deformation of the element, and of course, it is not going to the kinetic energy of this molecule or sorry the bulk motion. And we can say that this essentially is changing the internal energy of the system. It is not affecting the bulk kinetic energy, but it is affecting the internal energy. So, part of the surface force is instrumental for rate of change in internal energy, while the remaining part is along with the body force is instrumental in rate of change of kinetic energy. Oh. Now, as far as, so this is what about the work done, we have got the work done term. Now, look to the heat added. How can be heat added to a system? Heat can be added to the system by conduction, and any other form of heat addition at this stage we will neglect. At this stage we will neglect, because this is the most usual and or most common flow cases, that is the only thing which is important. Of course, in certain cases the heat by radiation, convection is already can be taken care of by the other process, because all these are convective acceleration. So, if there is a convective term, that convective heat transfer will automatically be taken care of in the rate of change of the energy part, because you are considering convection. By Eulerian description, you need not consider convection separately, it is always included. Of course, even in Lagrangian case also it is included, but it is little difficult to see. In the Lagrangian case, the derivative is simply d dt, partial derivative with respect to time. So, you do not really see clearly that the convection is also part of it. But in case of Eulerian description, because you express the material derivative is like in that way, there is a convective term. So, the convection is always included. So, other form of heat addition, like say heating effect through radiation or any other processes. So, that we are not going to consider here. I mean, you are not considering extremely high temperature, okay, at which stage many other processes are involved, that we are not going to consider. So, how much will be the amount of heat added? How much is the heat flux across a surface through conduction? How much heat can go out from a surface or come in, what go out or come in, whatever it is. On what it depends? Temperature gradient. Temperature gradient, okay, fine. And the rate of heat transfer is coefficient of thermal conductivity into gradient of temperature. Okay. So, this can be written again, say thermal conductivity, let us write K, okay. The gradient and once again we can express it as a volume integral by using that same divergence theorem, and okay.
So there should be minus sign because if temperature gradient is positive, so heat will flow out of the system.
But we have taken that we are considering that heat added to the system as positive.
So temperature gradient is seen from the side of system or towards the system?
We are considering towards the system, because you are adding heat to the system, that we have taken as the positive. If you look to that first equation we wrote for the first law of thermodynamics, in which we have added that d E equal to d q plus d w. Both we have taken what is added to the system as positive. Okay, what you are saying is correct. Usually this is known as Fourier's law of heat transfer, Fourier law of heat transfer, and the law is usually expressed in that form, q equal to minus k grad T. But because of our these notations we have made it positive. Okay. So, now we can write the complete energy conservation equation. Energy conservation equation, or in short energy equation. That first, the thermodynamical relation which is written for unit mass, we will write it as a rate equation, and we will also write instead of unit mass, we will write as per unit volume. Now, at this case you can see that this kinetic energy term from both the sides gets cancelled. The kinetic energy term from both the sides get cancelled. So, it becomes an equation for internal energy alone. However, this energy expression, as you will see later on, that they are expressed in various form. Okay. In certain form it is kept on both sides, okay. Rather this itself is written as something different, as total energy or something, this part. And also in many cases, instead of coming to this form, these two parts is written in this form itself. without doing this addition, they are kept like this. So, in various form they are expressed, but here we will just cancel them and write it in this form. The other forms we will not be writing. So, we have here the rate of this itself contains that convection. Okay. So, convective transfer of temperature is not required. Like coefficient of viscosity, this coefficient of thermal conductivity is also a function of temperature, and in case if it can be approximated as constant, then this k will come out and this will become simply Laplacian of temperature, this term. Okay. If k can be taken as a constant, in that case this term will simply become a Laplacian of temperature. Let us forget. Now, let us come to the first term, sigma I j du y dx j. We have many times already expressed du y dx j, that is the velocity gradient tensor, as sum of the rate of strain tensor plus the tensor representing vorticity. Du y dx j as sum of one symmetric tensor and one antisymmetric tensor, that we have been doing it many times. So, this we can again write sigma I j E I j using that same notations what we had. See, sigma I j xi I j, sigma I j xi I j is identically 0. Sigma I j xi I j is identically 0, because sigma I j is a symmetric tensor and xi I j is an antisymmetric tensor. What is sigma I j xi I j? For I equal to 1 2 3, j equal to 1 2 3, sigma I j xi I j will be what? Let us write it on this side. What is sigma I j xi I j? Here both the indices are repeating. So, it is sum over both, it is a sum over both I and j. So, this can be written as sigma 1 1 xi 1 1 plus sigma 1 2 xi 1 2 plus sigma 1 3 xi 1 3 plus sigma 2 1 xi 2 1 plus sigma 2 2 xi 2 2 plus sigma 2 3 xi 2 3 plus see, xi is a antisymmetric matrix, it is half of du I dx j minus du j dx I, and antisymmetric matrix. So, its all diagonal elements are 0. So, all these diagonal are 0, xi 1 1 is 0, xi 2 2 is 0. Now, see, sigma 1 2 xi 1 2 and sigma 2 1 xi 2 1, sigma 1 2 and sigma 2 1 are same, sigma is a symmetric matrix, xi 1 2 and xi 2 1 are opposite sign. So, they get cancelled, and see all these terms get cancelled. So, sigma I j xi I j is identically 0. So, this becomes only sigma I j E I j. express or replace sigma I j by what we have already found sigma I j. Sigma I j we have already found as minus p delta I j plus 2 mu look to this first term. What is this? P E I j delta I j, okay, minus P E I j delta I j. What is E I j delta I j? Yes. What will be P or delta I j E I j? E I j delta I j. You know delta I j is not 1 only when I equal to j, otherwise it is 0. So, it will become simply E I I. So, the first term is minus E I I, P E I I. What is E I I? Rate of expansion, rate of expansion or dilatation. Okay. Now, this entire equation is our rate equation. Okay. So, if we forget this, that rate, this is pressure and expansion. What is that? What in thermodynamics is usually called as PV work or compressive work, compression work. So, the first term gives that. More interesting is the second term. See, the second term can be written as, can you? See, it is 2 mu E I j okay, minus what is 1/3. Again here also there is E I j delta I j, which will again become E I I, and E I I in this case also you can write as E k k. E I I or E k k writing is all the same. So, this again become it will be quite a long term if we expand, it is quite a long term, but as you can see, why it is, how it is square? See, already we had du k dx, another du k dx we are getting from E I j delta I j. E I j delta I j is E I I, and instead of writing E I I, if we write E k k, it is all the same. We can change it. Any dummy variable can always be changed. I in E I is a dummy variable. It means E 11 E 2 plus E 22 plus E 33. The meaning of E I is E 11 plus E 22 plus E 33, and meaning of E k k is same, E 11 plus E 22 plus E 33. And what is E? E I is d y dx I. So, E k k is d u k dx k. So, that is what we have written. D u k dx k and E k k is same. So, either you write E k k square or d u k dx square, anything. And as you can see clearly, the second term can never be negative. The second term can never be negative, because this E I j contains this E 11 square, E 22 square, E 33 square, which is or one, the second term is simply 1/3 of E 11 square plus E 22 square plus E 33 square, and the first term contains E 11 square, E 22 square, E 33 square, also many other terms, which are also again square term. All the terms are square term. So, the second term can never be larger than this, and since all the terms present here are square terms, this second term can never be negative. Now, looking to this, what is this part of the work? Work done by what? Looking from here, this is what is that so called tangential stresses. This is part of the deviatoric stress containing only that part of the normal stress which sums to 0 plus the tangential stresses. So, this is work done by the tangential stresses or viscous shear stresses. And what you can see that this work done by these viscous shear stresses is always positive. That means, it is only one way process. It is only one way process in which only the kinetic energy moves towards the internal energy, that is the only possibility, and this energy, since we cannot get back, is basically lost. So, it is a dissipation. This term is called a dissipation term, and usually just denoted by a single symbol phi quite often. Again, do not get it confused with the velocity potential, because that is a standard notation used conventionally, phi for many things. So, this second term is always positive and is known as dissipation. The first term is the conventional or familiar pressure volume or compression work, PV work, pressure volume work, called as compression work, and in this case this is a useful work. Whatever work we give, we can get it back. Whatever work we use while compressing it, we can get back it while compression. So, here also you see that we have not introduced any further unknown except this thermal conductivity. Only this internal energy is the only additional unknown, or temperature which we set forth. So, there is no further unknown. What we had earlier, 3 component of velocity, pressure, density and temperature or internal energy. Now, we have that. Along with the equation of state, we now have 6 equations with 6 unknowns. Of course, 2 additional parameter mu and k, the coefficient of viscosity and thermal conductivity, which are usually a function of temperature, and if they are provided as a function of temperature, our set of equations is complete. Now, we have as many equations as there are unknowns. However, as before we mentioned that when the flow is incompressible, the temperature does not come through the equation of state. The equation of state simply becomes density is constant. So, there is no temperature and mu is also a constant. So, obviously, this energy equation is not at all required. In case whatever small temperature difference or small temperature variation is involved, if you want to find that, it can be done by solving the other set completely first, that is the combination of equation of continuity and Navier-Stokes equations together, find the velocity and pressure, use that velocity and pressure to solve this equation to get the temperature. That means, they need not be solved together, they can be solved independently, because you see that in those equations then there is no term which depends on temperature. The equation is completely decoupled from the energy equation and can be solved separately. Mu is then not a function of temperature. If the temperature variation is very small, say just about 50 to 100 degree type of temperature variation you are associated with, in that case mu can be taken as constant. Okay. A standard value of mu can be taken in that, and because even though temperature mu is a function of temperature, but the variation is so small with temperature that over a range of 50 or 100 degree temperature, the variation in mu is really negligible. Okay. So, that type of small temperature difference is not affecting mu. So, they can be solved separately, the equations, and once that solution is found, particularly the velocity field, because to solve this equation you must know the velocity. This equation contains all velocity, this E, they are all velocity. Even here also there is velocity. When you write this is in the full expanded form, there is velocity associated with it. So, without knowing the velocity, this equation cannot be solved, but the other equation can be solved without knowing the temperature. So, this you can also summarize that if the flow is incompressible, and temperature variation is small, the continuity and Navier-Stokes equations can be solved they are decoupled from energy equation. They are decoupled from energy equation. once they are solved for velocity and pressure u and p, energy equation can be solved for temperature separately. We will consider one or two small examples as for solving this Navier-Stokes equation. Particularly, I think you have already solved one or two problem using this Navier-Stokes equation. Okay. Without even writing the Navier-Stokes equation or perhaps knowing the name, perhaps you have not heard of the name of these equations, Navier-Stokes equations, but you derived a special form of Navier-Stokes equation for a special application and solved it. So, we will, as we mentioned already, that for the general case there is no solution. For some simple problems, for some very simple cases, some solutions are there, and of course, most of them we will leave for later, but one or two simple cases we will consider to look for the solution of the Navier-Stokes equations.